Fine. In the last class, we did look at the different ways in which the units of sound got transformed. Firstly, from the Pascal value to the decibel value, which is the logarithmic scale, and then above the decibel value, we had different ratings, the A, B and C rating, which was meant to capture the human factor of this acoustic engineering. The fact that we perceive different loudness for different frequencies is captured through this A weighting criterion. A weighting is the one which is like uniformly used, except for very sort of exceptional cases. You will mostly get to see the values of sound or noise rather would be reported in terms of dBA, and in particular if you recall the CPC noise regulations, the Central Pollution Control Board noise regulations are in terms of dBA. So, now you know what dBA means in comparison to dB. Okay. So, we will move forward and we will define a few more terms which are meant to incorporate the different factors as human factors associated with these ideas of noise and its perception. So, definitely the hearing damage potential that a person encounters when he or she is exposed to noise is going to depend not only on the sound level, but also on its duration. So, if you can have a higher level of sound, but if it is for a very small duration, then hopefully it should not be that much hazardous in comparison to a lower level of sound, but acting over a longer period of time, right. So, therefore, we need to now incorporate a certain more effects which sort of captures this effect, especially if the noise is transient. As we know, machines do not encounter a fixed load condition, they do change. For example, in our vehicle, as you change the speed of the vehicle, the engine operating conditions change slightly and the road noise obviously will change. So, wherever you have an intermittent operating condition and wherein it is not possible to say that the noise is steady, then you must have a record of this rather a measure of how hazardous the noise is, right. So, towards that end we are going to develop a few parameters by which we can quantify these issues of intermittent noise. So, the first factor which comes is called LEQ, that is somewhat like an equivalent sound. So, what we do here is that we understand that the logarithmic addition simply tells us to take the sum of 10 to the power LP by 10. You would have seen that that is how the sound addition was basically done. Let me just turn back to show you that formula. Yeah, something like this is the averaging formula. So, if you look back at the sound addition formula, which is this, yeah. So, when you have to add sound at different levels, you simply within the argument of the logarithm, you have to add 10 to the power LP 1 by 10, 10 to the power LP 2 by 10 and so on up to the n sources. So, now what we tend to do is that associated with each time interval, there is a different sound pressure, that is the idea of intermittent sound. Associated with different time intervals, you would be recording a different value of SPL. So, you cannot report a single value of LP, but rather LP itself will be a function of time, which is what I have meant by this notation. LP is now a function of time, and for each of these time windows, you will have to just instead of the summation, you will have to take an integration and divide it through by the number of the entire time interval of your interest. So, instead of the summation as you used in the decibel addition formula, you will have to integrate this out, integrate this over a period, but then normalize it again by having a 1 by t division and then 10 log 10 of that. So, that will give you the equivalent sound pressure level when the sound pressure level itself is changing with time, right. Remember, we had said that we will do harmonic calculations, we will take steady state, but this is an exception to that situation. This is not a steady state condition. Here we are accounting for the fact that in time sound pressure is changing and we have a record of how it is changing with time. Then this is almost like a dB averaging formula, but just that instead of the summation it is actually a integration. Other than that, the formula is all nice and fine. So, if we have to report the sound for a vehicle which is let us say running from 0 to 40 and then again from 40 back to 0, then as the vehicle is running at different speed conditions and maybe different road conditions also, then it will generate different sound pressure levels. We will take a record of that, put it in this formula, and then at the end of the day we will say that the LEQ of this vehicle or the equivalent sound pressure level of this vehicle is going to be such and such. But this is not what is asked for in a pass by noise. Pass by noise is much simpler, which we had discussed, but this is just as a matter of reporting and capturing the fact that it is an intermittent noise rather than a steady state noise. So, this is called equivalent continuous sound level or LEQ, and this is what will quantify the hearing damage potential in some sense, because it captures both the magnitude of the sound pressure level as well as time duration of it, because the integral of the the integral of the sort of mean square effect is properly captured and the average value is correctly reported. And then instead of taking these LP values directly in terms of decibel, if you take the LP values in a air weighted decibel scale, and you know what is the difference between air weighted scale and the standard scale is, then instead of LEQ we will have LAEQ. So, that is equivalent sound in the A weighting factor. So, that is also something pretty easy to understand. LX is a pretty useful measure. It is if we report, for example, in this recording studio, we wish to make sure, let us say that the background noise is less than a certain value, let us say 20 dB or so, right. What do I mean by background noise? Obviously, I can't say that even if I keep my mouth shut and there is no noise, if we have to take a measurement, the sound will not always be measured to be same, right, because the disturbances at times will be more. Some people in the corridor will be shouting at certain times, maybe at lunch time you will find people at the corridor freaking away, but at other times it may possibly be quieter, right. So, we need to have a measure, let us say 90% of the time what is the value of this sound that is recorded. So, that will be L90. So, if for example, L90 would be a background noise level, that means for the 90% of the time sound pressure level will exceed this level, right. So, if L90 is reported as 20 dB, that means for 90% of the time the sound level is more than 20 dB. Similarly, the converse situation, if L10 is reported as 20 dB, that means for only 10% of the time the noise exceeds 20 dB. So, that means that is a particularly quiet room. Only for 10%, let us say I have my house in a village and it is perfectly quiet there, it is far from the highway, and I report that L10 for that house is about 40 dB. That means only for 10% of the time the noise exceeds 40 dB, right. Whereas L90 would mean for 90% of the time. In an urban setting, I would rather have L90 to be 40 dB, which means for 90% of the time the value which will be exceeded is the floor which will be exceeded is 40 dB, right. For the 90% of the time the value recorded will be more than 40 dB, whereas in the first example for 10% of the time the value will be more than 40 dB. So, L10 is a more stringent measure. If you are reporting in terms of L10, it is a very aggressive and stringent measure. L90 is a very relaxed it is a relaxed measure, because you are basically reporting that for 90% of the time the sound will exceed this value, right. Okay. Just like we had this quantity LEQ and LX, we will again sort of change our game a little bit, and that is again dictated by a lot of experimentation on human subjects. And it so happens and that if the change in sound level is just 3 dB, then we are just able to perceive it, right. What has been shown by experiment, a lot of extensive experimentation is this, that what is a barely perceptible change in loudness is 3 dB, not 3 dBA, but 3 dB, right. So, 3 dB is the bare minimum change that you need to make in your product such that your customers are at least able to perceive a change in its acoustic characteristics, right. And 5 dB will be distinctly perceptible. So, if you really want to make sure that you win hands down in terms of improved acoustic characterization, you have to have a target of at least 5 decibels, right. In other words, if you just change by 2 decibels, probably 1.5 decibels, that will probably go unnoticed, right, in terms of the perception of your customer. So, the that actually makes the target pretty stiff. So, a bare minimum of 1.5 dB or 2 dB does not at all cause any perceptible difference. 3 dB is sort of the threshold after which you can change, have a perceptible improvement in the effect of noise difference. But what is distinctly perceptible is 5 dB, and again in terms of perception, a 10 dB difference is apparent to us as a half or twice the loudness. This is pretty strange, but that is how our human ear responds to it. If we play out sound at 2 different decibel levels, the values of which differ by a 10 decibel, and this difference is just a arithmetic difference. The arithmetic difference is 10 dB, which means 80 dB and 90 dB sound. Perceptibly it appears 90 dB is twice as loud, right. So, we need to incorporate these perceptions also in another new scale. Decibel we understand is not able to incorporate these perceptions that a 10 dB difference is half or twice as loud. So, we define this new scale which is called phone. So, phone is the SPL of an equally loud sound at 1 kilohertz. We have already seen the chart for equal loudness contour, right. So, this was roughly the chart for equal loudness contour. So, phone is the SPL of an equally loud sound at 1 kilohertz, right. So, 1 kilohertz, as I said, is just the reference frequency. So, here you will see that at this 31.5 an equally loud sound is about 40, right, at 1 kilohertz. So, 81 dB at 79 dB at 31.5 hertz is equally loud as 40 dB at 1 kilohertz, right. So, using that idea, this phone measure is taken in, which is the SPL of an equally loud sound at 1 kilohertz. So, if we have 79 dB sound at 31.5 hertz, the SPL of an equally loud sound is actually 40 dB at 1 kilohertz. So, the phone is 40, even though the dB value is 79.5, the phone will be just 40. Okay. And to get into this effect, that a 50 phone sound will now be perceived as twice as loud as 40 phone sound, because basically phone is SPL measured in dB. So, we understand, just as an example, a 50 any 10 dB difference will now be equivalent to a perception of twice or half the loudness, right. So, 50 phone sound essentially means an SPL of 50 dB at 1 kilohertz. 40 phone sound essentially means a sound which is equally loud as 40 dB at 1 kilohertz, and these two sounds will have a perceptible difference of being half as loud or twice as loud, depending upon which way you look at it. So, therefore, to capture this effect of twice or half, we invent this new scale which is SON, right. So, SON will be 2 to the power phone minus 40 divided by 10. So, if you now see put P as 50, then the SON associated with the 50 phone sound is going to be 50 minus 40 by 10 is 1. So, SON is going to be 2, right. For a 40 phone sound, the SON is going to be 1, right. So, now we have calibrated this perception correctly in terms of SON. So, a 40 dB sound, a 50 phone sound will appear in Sohn's scale as 2 Sohns, right, whereas a 40 phone sound will appear as 1 Sohn. So, therefore, you get the feeling that the loudness has doubled for a 50 phone sound than in a 40 phone sound. So, these are all lot of nitty-gritty details have been incorporated just to capture the idiosyncrasies associated with human factors, the human perception of hearing, and still lot of active research is continuing to incorporate these effects even better. But I think this is where we will sort of let it go, but probably with one more example. Again, in case of intermittent noise, let us say for an air conditioner works with a or refrigerator, for example. These days the compressors are far more silent, but at least maybe if you look at those refrigerators 10 years back, they used to have a very noisy compressor, and once the compressor used to get switched on, then there will be a huge noise, impulsive noise, because of that compressor starting to work. So, that is an intermittent noise. You do not want to quote the noise of a refrigerator. So, both of these conditions are like an extreme condition, that is the extreme noise will be heard when the compressor is just switched on, and if the compressor is switched off, again you will have the lower limit, right. So, a manufacturer, a refrigerator manufacturer cannot possibly quote one of these two extreme noise and get away in terms of its favorable or unfavorable situation. What one has to do in such cases is that one has to quote the noise rating associated with the machine. So, noise rating curves are sort of standardized curves, and this is one such graph. This has been taken from the textbook by Bias and Hansen. So, this what we do here for quoting the noise rating of any particular industrial component is the following. So, as you note, the x axis is in terms of octave bands. These are in all geometric progressions. These are the center frequencies of different octave bands. So, we will measure out the octave band SPLs on using certain instruments, which we will talk about how to measure the noise, but we will plot these SPLs as a function of frequencies taken in octave bands, right. And then we will find out which of these curves encloses the plot under all conditions, right. We understand that the frequency spectrum can possibly change, because it is an intermittent noise, it is not going to remain in steady state, it is an intermittent characteristic. So, we will keep taking under all possible condition, compressor on, compressor off, and whatever other conditions that you can think of. For all possible conditions under which this machine is supposed to operate, we will have to take the readings for the SPL as a function of its octave band frequencies, and then overlay on this noise rating curve. The curve which just encloses this entire spectrum, I mean spectrum for all possible such conditions, that will be quoted as the noise rating of this machine. So, it is a pretty aggressive criteria that you have to when you quote the noise rating, and typically I think a few days earlier I bought a juicer mixer, a food processor kind of thing. When I read the manual, it quoted the noise rating value, the NR value, right, that was nice to see. So, this is where, because in the juicer kind of application, food processor kind of application, you have intermittent noise as opposed to a steady noise, right. So, in such cases these NR values have to be quoted, and as I said, they are useful for quantifying intermittent noise in products. But again there are various incarnations and various avatars of this kind of graphs. Noise rating or NR is one of them. There will be similar depending upon the standardization issues, the other conventions also are there, which are called noise criteria, balanced noise criteria, room noise criteria, and so on. Each of them essentially gives you one such chart, but the process of arriving at the NR or the NC number is exactly the same. Take the reading, overlay it on these curves, and find out which is the highest curve which just encloses the entire spectrum in octave bands. If you can do that, that value is going to be the appropriate NR or NC value. And the reason why we have different ratings is because that in different situations you have different perception of sound. For example, in room you will have a room which is pretty large. It is having, or in auditorium acoustics case, the perception is going to be very much different than let us say in my small living room where I have a refrigerator. So, therefore, you will keep seeing different conventions as per the different applications that are being used. Noise rating for some reason is sort of quite well known for home appliances and things like that, but there are other criterias also, and each of these criterias have evolved for a particular reason, which is mainly dependent on applications. Okay. So, with that I think I will close my discussion on human factors of engineering. By no means this is an exhaustive account of it. There are many more issues associated with human factors in engineering and in acoustic engineering, and it is an active field of research. Even as we talk, there is lots of work that is going on, which mainly deals about experimentation and trying to find out how we perceive sound, and then to develop ways and means by which we can incorporate these human perceptions into our instrumentation, and thereby have a testing procedure which reflects the perception of human perception of sound, rather than just quoting a Pascal value or the pressure value, because that possibly does not relate to our perception of loudness, right. Because as I said, the perception depends upon how our ear canal sort of picks up those signals and get them interpreted by the brain. Okay. So, there is a lot of anatomical issues which complicates the perception of sound, which cannot be sort of dealt with in this course in any further details. Okay. So, I will switch gears now, or maybe one more. We have one more, just one more slide associated with this, which is about industrial noise regulations. Yeah. So, as we said, the level and time of exposure of noise is accounted for determining its various hazardous impact, because one such thing was LEQ standard. The LEQ measurement was hopefully able to capture the level and time of exposure, but then LEQ is little complicated to calculate, because you will have to essentially take a record of the entire sound level for the entire period of time, and then do an integration, which typically factory people will not like it, right. So, you need a easier, simpler formula, yet which captures this issue that you have to account for both the sound pressure level as well as the time of exposure. So, as per this convention, which is Occupational Safety and Health Act, I guess that is called OSHA 1970, and I could not find a revision of it, but that is so we will stick with OSHA 1970. So, as per that convention, it was found out that a healthy human can possibly be exposed to 85 dBA of sound for about 16 hours, 90 dBA of sound for about 8 hours, 95 dBA for about 4 hours, 100 dBA for about 2 hours, 105 dBA for about 1 hour. Please note that in terms of time it is halving, and in terms of dB you are having a 5 dB change in difference. So, that is what we said even in the last slide, when we said a 5 dB difference is what is like roughly 5 dB difference is just about perceptible, but in actually in contrast to what to the calculation of phones and sones, where we said the loudness is in terms of is like doubling in terms of perception, but here this is the time that is permitted for exposure towards these noise levels without causing any health hazards. So, as per this standard, if you have a factory wherein let us say your steady state sound or LEQ is supposed to be 85 dB, then you have any worker can be permitted to work in double shift up to 16 hours, but if it is 90 dB, it is only 8 hours that a worker should be exposed to. And especially in the western countries, these rules are pretty stringently applied, and there are some tests and clearances that has to be obtained, and the worker cannot be subjected to more than these sound levels for these time periods, right. And if the value cannot be read off from this chart, you can use this formula, which basically is given by this. So, this gives, if for example, you have an 87 dB sound, generated in a particular environment, then the time of exposure for this 87 dB sound without causing any health hazard is going to be read off using this formula, right. Roughly it gives you the same, I mean it gives you the exactly the same values which are quoted in this table. So, you can see that if LP is 90, then 90 minus 85 is 5, 5 multiplied by 0.2 is 1, and then 16 divided by 2 is 8. So, that is how it goes. So, the factor here is of time is getting halved, right. This is the time that is permitted without causing any health hazard. This is not exactly loudness, this is the health issue in terms of both physiological and psychological issues associated with noise exposure. So, the point is this, that there is a factor which is called noise dose. Okay. So, the noise dose is given by this, the formula, which if in a particular environment like let us say in IIT in Gajendra circle you may have a different value of sound pressure level. At my office room you will may have a different value of sound pressure level, at the playground you will have a different value of sound pressure level. So, you will have to calculate the total noise dose, which means that the numerator of each of these factor is the actual exposure time to each of these noise levels, and the denominator capital T's are the exposure limits as given by these OSHA regulations. So, the total value of this noise dose should be within unity. So, instead of having just a steady state noise at 85 dB, you may have an intermittent noise of 85 dB for 50% of the time and 90 dB for 50% of the time, in which case you have to calculate the noise dose for that particular environment, and if it exceeds the value of unity, then as per OSHA that environment is not a healthy and conducive environment as far as the health issues associated with this noise exposure is concerned. Okay. So, again this is one more case where we have talked about human factors of engineering, the factors which decide as to what are the, how we can control the amount of exposure of noise and make sure that the inhabitants associated with a particular community are not subjected to any health hazards due to this exposure to noise. Okay. So, now we move on to the next topic, which is about experimental acoustics. So, here we will learn different instrumentation procedures associated with acoustics. The first important thing that we have to learn while taking our measurements in acoustics is that acoustic measurements cannot be just taken in any random situation. There are specially designed chambers which are called acoustic chambers, wherein we should take such acoustic measurement, and that is not because of some strange egoistic reason. There is a good reason why we have to use acoustic chambers. As we have known very well by now, is that the boundary conditions in acoustics can really cause a lot of difference in the perception of sound. If you have an enclosure, then the sound is not allowed to escape, and that it will keep reflecting back and keep reverberating back, and you will possibly hear a different sound than if the same product was there in free field. In the free field, you will not hear the reflected sound, you will only hear the incident sound, right. Whereas, in an enclosure, you will not only hear the incident sound, but also hear the superimposition of the incident sound together with the reflected field, and that reflection can be pretty complicated to analyze if the room is not a very standardized room or something like that. So, therefore, we need to, but at the same time it is not possible for a product to be always taken into a free open atmosphere and do the measurement. In fact, if I take the vehicle some like this and into the open road and open ground and try to measure the acoustic performance of this vehicle, the problem is my noise measurement will be corrupted by the outdoor noise also, right. So, it is not possible to actually take this the product for which you want the acoustic measurement to be done out into the open atmosphere and take a measurement. That will require you a big open field wherein the outside noise does not contaminate your measurements. So, what is done is this, that you design something called an acoustic chamber. So, these acoustic chambers have acoustic absorbers padded in the 4 walls as well as the ceiling. However, it is not possible to do this acoustic absorbing lining on the floor, because if you do it, then there is no chance that the vehicle can be moved into this room, right. So, such rooms are called semi anechoic or hemi anechoic, because it is the reason it is called semi anechoic is because all but one floor is left without the acoustic treatment, and the work of this acoustic absorber is going to be such that it will absorb all the incident sound that is incident on these walls, right. And by the construction of it, it's a there is a reason why they have this wedge type construction. I will just sort of intuitively hand wave an explanation. You would have heard about Ferry's black body in your high school optics. So, this is supposed to be a black body wherein which will absorb all the light, and the reason it is of in this shape is, if you will remember, is that any light that is incident on it will keep going through having multiple reflection, and but with each reflection it will decay, right. A similar effect happens with these wedges that you see here. So, the wedges create this Ferry's black body like a situation here. The wave that is incident onto the wedge gets mostly absorbed, the part which gets reflected will now get incident into the neighboring wedge, and again the neighboring wedge will absorb the remaining part, and with a few reflections hopefully you can achieve a near perfect absorption. So, there are benchmarks associated with these absorbers, and these absorbing materials must follow suitable guidelines such that near complete absorption takes place, because then if a complete absorption of the incident wave does take place, you will have the situation of a non reflecting condition. So, that is as good as saying that you are in the free field, because there is no reflections. The only thing that happens is the incident wave, reflections never come back. But at the same time, this room also isolates any acoustic disturbance which may be happening outside the room to penetrate into the room, because this is a room after all, and these isolations together with the concrete structure of the room will ensure that the sound which is outside the room does not percolate into the room. Similarly, the doors and the windows here are, there are no windows in acoustic chambers, the doors are appropriately sealed, because if the door does not have a sealing, then the sound from outside will leak through the small slits that are there in usual doors, right. So, when we take measurements, we will shut this door, get the sealing appropriately done, and then we can expect not only will the inner sound escape outside, but also the outside sound does not interfere into the interiors. So, it is actually a reciprocal thing. If the outside sound cannot escape, if the sound inside the room cannot escape outside, the outside sound also cannot penetrate into the room. Okay. So, that is how we take the measurement. So, semi anechoic chambers or hemi anechoic chambers are commonly used for products that we would likely to be interested, but there are fully anechoic chambers also, where even this floor sort of is having an acoustic treatment. Obviously, as I said, you cannot bring a car in such a room, but if you are interested in let us say speakers, loudspeakers, right, and you really want to get the complete anechoic condition for the sake of your calibration, then possibly in such situation it makes sense to have an arrangement where, after all, a speaker is not that big, you can tie it up in some sort of a pulley arrangement and make it sort of hang in mid air with the help of a pulley arrangement, but then the sound that is emitted will be enclosed within a completely anechoic space, wherein only the incident waves exist, the reflected waves are not going to corrupt. So, at least in such sort of products we will have situations for fully anechoic chamber. However, for most industrial purposes, I would think that it is semi anechoic rather than fully anechoic chamber which will be more useful. Okay, as I said, it simulates the free field or non-reflecting condition in the indoor laboratory. It eliminates the measurement errors due to environmental or outdoor noise. The outdoor noise cannot corrupt the measurements done indoors. As I said, all these 4 walls and the ceiling are packed with these acoustic absorbers. Okay, and the instrument that is required to measure these acoustic or sound pressure levels is called microphone. By the way, there are different kinds of microphone. It is not just instrument for measurement of sound, but for example, recording of sound is also done using a microphone. Communication, your mobile phone, it also has a microphone. The essence of it is this, that the acoustic pressure, just like as it hits our eardrums, it is converted to an electrical signal which is interpreted by the brain, which is the boss of as far as the processing unit, human processing unit is concerned. The same thing essentially happens in a microphone. Whenever these acoustic pressure waves is incident in a microphone, using some techniques, it is converted to a voltage signal, and from there on it can have different purposes. When it is for your telephone, then this voltage signal is essentially transmitted through your carrier wave, which is what your service provider gives you, and then that wave is sent to the receiver, and then the receiver has ways and means to demodulate the carrier wave frequency and the frequency of your speech, and you hear it readily, right. Each of these application, whether it is communication, whether it is recording, they will have different kinds of microphones, that is understand. The microphone that I am using is here right now is for the recording purpose. This is not meant for measurement purpose, right. We are going to concentrate on the measurement part of it. Each microphone will have different characteristics. The measurement microphone is what we are going to look at it in this and the next talk. So, those microphones are called the condenser microphones. We will talk about those condenser microphones possibly in the next class, but let us just quickly give you some introduction about the requirements and the parameters which characterize the microphone. The one important requirement of a microphone is that by placing the microphone, you should not distort the sound pressure field. Just like if you have a flow meter and you are interested in measuring a flow through a pipe, and the fact that you are putting a flow meter in this pipe distorts that flow field, then it will be an erroneous measurement, right. Similarly, if you have an object which is sort of which is facing these sound waves, then the fact that there is an obstacle towards it essentially distorts the sound field. This distortion is technically called scattering. Let me just explain myself a little better. So, you would know, at least again to give the analogy from optics, you would know that if there is a wave that is incident onto an object, just behind the object you will have the a region of shadow. There is no light which will pass through, but maybe this light ray will pass through. So, at some angles you will be able to see that the optic field is undistorted. So, the moral of the story is this: whether I place the object or whether the object is absent, the field that I wish to measure is going to be different, right. The difference is going to be very minimal if the size of the object is very minimal. For example, as we are talking, we are having some dust particles definitely in these rooms, but these dust particles are so small, possibly they do not scatter or they do not create an obstruction, right. But then similar thing can happen even for acoustics. So, if you have let us say an acoustic plane wave and you wish to measure this condition wherein the acoustic plane waves are set up in a particular environment, the fact that you are bringing in a microphone, right, and what is the condition that this solid object will demand. Let us say this microphone is made out of a rigid solid material and the microphone does not start vibrating, the body of the microphone does not start vibrating. The microphone is actually placed on a tripod stand also, and you can feel that the tripod stand is pretty much rigid, right. So, if it is rigid, then what is demanded is all along the body of this microphone, you must have a 0 velocity condition, right, because the microphone should not is rigid, it will not vibrate. So, therefore, it demands that the particle velocity of the microphone particles which are in neighborhood with the air particles surrounding them should have a 0 velocity, right. But then that is not possible, because you have a plane wave condition, every particle should vibrate. So, that means the fact that you have introduced another instrument in the field definitely means that this field is going to get distorted, right. It is not going to remain a plane field, plane wave, or if it was spherical wave, even that is not going to assure you that you have 0 velocities exactly at the boundary of your solid surface, right. Because your instrument is like a rigid solid, it is going to demand that all along the boundary of your instrument surface you should have a 0 velocity. That is not possible. So, therefore, you the incident field will get distorted, and that distortion is called scattering. And there is a whole lot of theory as to how you can find the scattered wave field because of the presence of some scatterers. We will not go into that, but just again from analogy with optics, we will make this remark that if the scatterer is really small, then the effect of this distortion is going to be minimal. But then there is nothing like small or big, it is always small or big with reference to something. So, if the scatterer is small in comparison to the wavelength of the sound, then you can have this condition that the effect of this presence of this scatterer is going to be minimal. It will scatter the sound in a minimal fashion. So, you could almost neglect this scattering effect in case it is small. So, one of the important conditions that is demanded for good acoustic measurement is that the presence of the microphone should not distort or scatter this acoustic field, and this will actually imply that your microphone should be small, right. If the microphone is small, you will be able to satisfy this condition, I mean small in comparison to the wavelength of the sound that you are measuring, right. So, therefore, you will see microphones coming in different sizes. Please understand, the smaller size is better in terms of scattering, but smaller size will be worse in terms of sensitivity. So, these are the two competing factors which goes for your microphone selection, and through this and possibly the next talk we would like to understand these concepts, that how do you make a proper selection of microphone. There are different kinds of measurement microphone available. I mean there are two main kinds, I should say. One is called the pressure field microphone, the other is called the free field microphone. Actually, pressure field microphone works under the condition that the sound pressure will have the same magnitude and phase within the field of your measurement. So, that is possibly true only when you have a small enclosure, something like a Helmholtz resonator, right. A resonator which is like a cavity, and that cavity, if it is very small, then again small in comparison to the wavelength of the sound, then you can assume that all points have practically the same pressure and the same amplitude of the pressure and the same phase of the pressure. In such situations, pressure field microphones are supposed to do a good job, whereas the free field microphones are the ones that we should use, which will work better in an anechoic chamber, which is in a free field setting. So, these are suited for a free field setting, a setting wherein you have only an incidence wave and nothing else, the reflected wave does not come back. Whereas, pressure field or random incidence microphone generally assumes that it will work in a setting where there are multiple waves all combining in such a fashion that the phase in case of a random incidence microphone is going to have the same value at all possible points. Whereas, in a free field microphone it is going to be under the setting that there is a single wave, right, and if there is a single wave that is going on, then obviously the phase associated with different points will be different, right. And the fact that you are talking about a free field situation, which means that you are talking in essentially about a condition where there is a single incident wave. The way in which things will get now complicated is that for a free field microphone, the orientation of the microphone matters, whereas for a pressure field microphone the orientation does not matter, because anyway it is supposed to work under the condition where all points will have the same pressure and the same phase. So, it really does not matter how you hold your microphone, whereas a free field microphone will work best, and it is suggested that the way you hold it is such that the diaphragm or the front face of the microphone actually faces the normally incident wave, right, because that will what cause the maximum that will cause the maximum response of the diaphragm of the microphone. I will just explain myself with one picture. So, essentially a microphone will have a diaphragm. If you have a sound wave which is incident directly on it, then the entire pressure, the pressure surfaces as we know are going to be normal to this incident direction. So, on the diaphragm you are going to have the sort of uniform pressure at any instant of time, right, but between different instants it will fluctuate, but at a certain instant it will be uniform. If instead on the microphone surface you have, let us say, the other extreme where the incident wave just traverses tangentially, then what will happen is that this point will have a certain pressure, whereas the neighboring point will be at a different phase, right. There is a phase difference between this blue and red. So, therefore, the pressure associated with this blue plane and the red plane will be different. So, different points in your diaphragm will see different phase of the pressure, whereas here the diaphragm was being loaded by a constant pressure across its entire surface. Here you will see the diaphragm will be loaded by some kind of a harmonic pressure, right, which will sort of complicate things, which will lead to erroneous measurement, because the calibration has been done, the sensitivity charts has been done for a uniform pressure impinging on the diaphragm surface. So, therefore, for free field microphone it is imperative that you use this microphone with the knowledge that it is supposed to work best when it is pointing directly along the direction of the incident wave. It should not point the other way around, okay, or it should not point in a perpendicular direction, in which case you are going to have erroneous measurement. Okay. A free field microphone, if we use this free field microphone in a diffuse field condition, if we make this mistake of using this free field microphone in actually a situation where there are multiple waves and the phase is all random, then the measurement that will be obtained is going to be underestimated, and rightly so, because it is not sort of having the capability to factor in this effect that the phase, there are multiple reflections that are coming in. Free field microphone is designed on the basis that there is only one wave, the incident wave, which hits the structure. So, as per that the calibration and the sensitivity charts will be made available to you. So, if you use in the condition of an enclosure, and in an enclosure which is small and such that there are multiple reflections happening, then these multiple reflections will actually not be properly accounted, resulting in an underestimation of the measured SPL values. So, I guess we will leave it at here, and we will take a deeper dive into the way microphone different parameters of the microphone work. We will actually derive the sensitivity of a condenser microphone for you, and we will show you the attributes of a good, what we think is a good microphone for at least the testing purposes. But as I said, depending upon the applications, the microphones differ, depending upon the economics the microphone differs. For example, in a phone, obviously the microphone has a different purpose, different economics. In this collar mic it has a different economics, but essentially the microphone is anything which can convert this acoustic pressure signal into a voltage signal. So, to that extent we must understand that this is the generic use of microphones, but we are interested only in the testing, acoustic testing microphones, not anything else. Okay, thank you.